Hey, Previn. First of all, I want to thank you for doing this for me. And this video is like it's not like the presentation. It's just me explaining to you like the work in this presentation. And also like predict some of the questions that I think people might ask, and also to explain the answer. So I think you have a overall idea about my research, right? So my research is about target defense game with faster and slower defenders. So this paper is majorly, well, it is about slower defenders, and I consider about the problem where there's only one defender, one slower defender to protect the target area. So this problem is kind of very much less studied. The slower defender problem is much less studied than faster defender problems. And the solution, I think, I feel it's kind of weird compared to faster defender solutions. So I think I've made a lot of effort trying to explain how the problem is formulated and what's the difficulty it is there regarding the slower defender game. So I think I've use a lot of space in this slides to explain the problem description, and the main part is about how slower defender makes a difference, and also because my goal is to solve the barrier, but the method I used is that but the way I solve it is start from the optimal trajectory. So the solution for the optimal trajectory is already there. It's not my novel work. So that trajectory is solved by a paper authored by this guy. If you search for Haig Dawn, two defenders, I believe you can find this paper. It's written in 1976. This is like a pretty old, early work. So if you Google it, you should find it. So the optimal trajectory is solved in this paper actually. So I kind of only use it to solve the two slower defender games that I proposed in this paper. So well, like in conclusion, I use this existing solution of the optimal trajectory to solve for the so-called barrier um, of these two games. Yeah, so I will explain the barrier a little bit more later in the video. And this optimal trajectory, I think is kind of, for me, it's a little bit hard to understand. It take me like a pretty long time for it to start to make sense. So I spend more time, I think, and more spaces in this slides to explain like the optimal trajectory. So actually, as long as these two things are explained clearly, I mean, there's two things. I mean, why slower defender is worthy of study, and the second is the optimal trajectory. How does it look like? Its features, things like that. So after these two things are explained, I believe the solution is much easier to understand. So that's why this part take a larger space and larger effort. Yeah. So yeah, that's just something I wanna let you know. So here is like the main content. So first is a background. Yeah, I believe you are very good at storytelling, so you can tell it well. So basically, it's about the increasing concerns that brought about by the drones. So if you want more details, you can just Google counter UAS systems, or like in my thesis, they are like pretty a lot of papers regarding this topic in my references. So it's basically about like the drones are showing up in lot of areas like government buildings, military bases, and airport, like putting threats to those places and people. So we want to detect and intercept those drones. And there's a specific technology here called the counter-UAS technology. Um, but those researchers are basically focused on two aspects. The first is to how to detect those drones. Um, like the challenge is that like drones are much smaller than like commercial aircraft, right? So the current radar system is I mean, radar system is kind of hard to detect them. So yeah, there are some specific challenges there, just for the background information. So it's an active topic, and that's the first thing. The other thing about counter-UAS technology is that people are studying at how to intercept those drones. For example, showing here is one of the methods, like ejecting a let. There are other methods that intercepting drones. So this is the other topic that is actively studied in this counter-UAS technology area. But like for my research, I'm looking at different from a different perspective. So I assume the previous two things are already solved. I mean, like we know how to detect the drone, so we know its locations, and we also know how to intercept them once they get in range. But the problem is that what if the invading drones are out of the range of the interception device when they are detected? So there's a gap between the detection range and the interception range. So in this case, the defenders might need to move actively, like they need to decide a strategy so as to get those invaders in range. So kind of my study is to fill in the gap. So given the locations of the invader and the defender, we need to know how the defender should move so as to get an invader in range. So that's the problem that I want to solve. So this picture, like this page here is talking about more like a general target defense game. Um, so here are the assumptions that I use. The first is that I assume the invaders are smart. So this is the key point that makes this problem a game. Because if the invaders, if we assume they are like moving along predefined path, or assume them are moving randomly, so that will not make this problem a game. Because kind of we know if we assume a known behavior of the invader, then we only need to solve the behavior of the defender, right? So that will not be a game. So a game is like both defender and the invader can make their own strategies. So if the invader moves differently, then the defender must adjust their strategies as well. So that's the first thing. And the second thing is, oh yeah, the reason why we make this assumption is that we want to handle the worst case scenario. Like if even though the invader is doing its best, we still want to be able to handle the situation. Okay, so the second assumption is that we use single integrated dynamics. So I put the dynamics here. It's very simple. It's kind of I feel like it's too simple compared to what you guys are doing. Like you always use much complex uh like dynamics. At least it's double integrated, right? Or unicycle model. So I think this is might be the point that people might ask questions. So my answer or my defense to that is that almost like a large portion of the studies about differential games, they all make this assumption. It's just if we use a little bit more complex model, then you just cannot find a solution. It's like too complicated. So actually, also like The defense also works for the third assumption that we assume perfect information on positions and velocities. So this is also to simplify the problem, and a lot of papers in this area use to make it possible to get a solution. Actually, possible to get an analytical solution in many cases. Also, it's just like simplification a lot of people use. I think that could answer the questions if someone asks. Yeah, and also I assume non-zero capture range. This is like there are many studies that assume r equals to 0, so that will make this problem much simpler. So here is like a more complicated assumption that I use to formulate the problem, especially for slower defenders. Okay, so this page is about the dynamics and the goals. I think you are familiar with this one. Invaders want to enter target area without captures, and defender want to prevent the entering. And on this page, I also want to explain something about this optimal. So it's more like an equilibrium. That's the solution that I find. It's kind of like it contains both the structure of the invader and the defender, and it's like an equilibrium because nobody wants to make a change. So if the defender deviates from the solution, it's just not beneficial for the defender. So the invader can be better. It can like enter the target area easier or take in short time, things like that. So if only the defender deviate from this optimal solution or equivalent solution actually. So nobody wants to make a change. That's basically what it means by this optimal solution. So that also means like if the invader deviate from this optimal solution, then the defender can do better, right? So that means the defender can only do better. This no like if the defender follows the optimal solution, that's the best it can do. Right? So yeah, so this is a little bit more like explanation about optimal. Um, Yeah, so at this page, I'm going to explain the things about why slower defender is like fundamentally different. Makes why slower defender makes a fundamental difference. So the reason is here, um, because it looks like the faster defender can always win the game if there's only one defender. Because the invader can just enlarge the distance between itself and the defender, right? You can just run away. So when the distance between the invader and the defender is large enough, then the invader can just directly go into the target area. So if you just when at your first glance of this problem, this might be what you think. That's what I think at the first time when I think about the problem, right? So it feels like the invader is naturally always win the game. Also, more specifically, um, at least there is a strategy showing here that invader can do. So even though the defender has reached the capture range, um, the invader can like because it's faster, right? It can use part of its velocity to match the velocity of the defender and use the rest to rotate around the defender. So that way the invader can keep its distance between itself and the defender. So it won't go any closer. It can keep this distance. Um, so yeah, actually, a little bit more detailed thing about my problem formulation that I require like the distance between the defender and the invader to be smaller than the target than the capture range. I assume this as capture. I define this as capture. So if like the distance between the players are is exactly equal to r, then this does not count as capture. So by using this, I call it rotating around strategy or loop around strategy, the invader will not be captured even though it's like has already reached the capture range. Okay, so once the invader start to use this strategy, I will say that I would define this as the game has entered the so-called loop around stage. Okay, so this is about how the defender, how a faster invader like makes a difference. It's easier for it to win. Um, so because of this, the optimal trajectory, as I mentioned, which was solved in 1960s, because of the specific strategy that the invader has, the optimal trajectory of this problem will have a specific structure. So first of all the players will move along straight lines. This has already also been proved in existing work. So basically, for this dynamics, if you follow the theory of differential gain, you can always prove that the trajectories are straight lines. So if we are dealing with a faster defender problem, then the whole trajectory, all the optimal trajectory are completely straight lines. But for a slower defender, because of this rotating around strategy, those straight line optimal trajectory will only last till the point the capture range is reached. Because at this moment, based on my definition of capture, right? Here is the definition of capture. So the straight line strategy will maintain until this point. So from the start of the game until this condition is satisfied, the optimal trajectories are straight lines. And then the invader is going to switch to this loop around strategy to prevent this thing from happening, which means not captured yet. So from this moment on, the trajectory will be like a curved trajectory. So I call the second stage the loop around stage. Or like stage one and stage two. Stage two is this loop around stage. Okay. Yeah, so if you look at the picture here, because we're talking about the possibility of capture or defender target hero with a single defender, right? So I've shown here in this picture the possibility for this defender to succeed is that either like there's a wall or there is another defender coming in, so this defender can cooperate with the other defender, but we are not going to talk about that in this presentation. So but we will consider about when there's a wall. So in this case, we can feel like that the defender is gonna take advantage that the invader is going to rotate around it. So it feels like the defender is trying to push the invader because it knows that the defender will move along, like move with it, right? So the defender trying to push the invader closer and closer to the wall. Then it can take advantage of the existence of the wall to capture the invader. But if the defender like push it too hard, I mean, if it use too much velocity along the direction of pushing the invader, the actual result will be like not as good because like let's assume the invader is originally at this location, right? For the invader to win, it needs to rotate to the other side of the defender. And then you can just go inside the target area, right? So if the defender push it too hard, if it use all of its velocity to push, then the invader can actually rotate faster to the other side. So to prevent that from happening, the defender, it kind of leads to recede toward the target area a little bit. Well, this is not beneficial, right? But like if you only look at like receding toward target area, it's not that beneficial. But by doing this, it can make it possible to push the invader to larger extent. So kind of this is a balance and the trade-off here. So the optimal trajectory actually is a good balance, is the best balance between those two effects. So I put it here. The defender needs to balance these two effects. Okay. So well, this another thing that I want to explain is that actually I also put it here. Like at this page, we only talk about the first possibility of the defender to win the game, right? Which is when there's a wall. There is another possibility here. To describe that, we need to explain the balance between the invader. So you probably have already find out that on the one hand, the invader needs to like enlarge its distance from the defender, right? To go along the let's say if this is the target area, the invader needs to like to go parallel to the tangent direction of the target area boundary. So that's the first thing that the invader needs to do. And the other thing is like it needs to go closer to the target area, right? So the invader needs to balance these two things. So if we imagine that when the target area is a straight line, then the invader only needs to specify, like to allocate infinite small component of its velocity, then it can move closer to the target area, right? But if the curvature of the target area is larger, like if it's like this, then the invader needs to spare more velocity towards the target area to have the same effort to have. I mean, like if the boundary of the target area has like a larger curvature, it's not straight. If the invader still use all of its velocity to go to the right, then it will be like faster, more like further and further away from target area, right? So it needs a certain amount of velocity towards the target area only to maintain the distance between itself and the target area. So if the curvature of the target area boundary is larger, then it's harder for the invader to get closer to the target area, right? So between the two things, that like the optimal trajectory is also the balance of these two aspects of the invader. So because the curvature makes a difference, that means when the target area is small enough, like getting closer to the target area is too hard, then at some point the invader will be impossible to do it, and the two players will end up rotating around the target area. And then the invader just it just cannot allocate large enough velocity towards the target area to make it getting closer and closer to the target area. So that would give us the second scenario, second possibility for the single defender, slower defender to win the game. So that's the second case that we're gonna discuss in this paper. Yeah, okay, um so on this slide, I just like I want to emphasize on the balance that the defender and the invader have to like make trade-offs. Okay, so I think at this point, I hope I've explained clear like uh what the structure of the optimal trajectory and like why and the challenges of slower defenders and why we want to study these two cases. And then we want to come to the solution. So as I mentioned before, we've already known the optimal trajectory, right? So now we want to solve for the barrier. Well, it basically means, so in those two figures, I just wanna, this is just a rough expectation, what we will have. The exact solution will come later. So that's why I put a question mark here. Um, so for fixed, oh, by the way, I call the wall the deadline because once the invader touches those wall, then we count it as the invader loses the game. So it's kind of the invader will die if it touches the wall. So it's also called the deadline. So the name I use the name comes from Isaac's book. So Isaac's is the guy that initiated the differential game theory. Yeah, so I just adopt that name from his book. So just a little bit of explanation, just in case anyone asks. So I use this parameter L. Why is LB? I don't know. Is it LD? Anyways, this parameter is the distance between the two deadlines. We take this as a given parameter, and then we will fix the location of the defender. And what we want to solve is this barrier. So if we can solve the barrier, this is how it works. If the invader starts here, then the defender don't need to move. So if the invader wants to get inside the target area, it should like move somehow like this, right? At the moment the invader touches the barrier, then the defender has to move. Because if the well, let me say this again. So if the invader starts from anywhere above the barrier, then the defender can win the game. But if the invader starts from anywhere below the barrier, then the defender will lose the game. So if the invader starts from like on the barrier, then the invader will be captured at the boundary of the target area. Okay, so this is the barrier that I think should look like, and also, well, the final result for this one will not look like this. This is just an illustration to show that there is a barrier here. Okay. I put it here, given the different location solved for the barrier. So in order to explain the solution, I want to explain a little bit more about the optimal trajectory here. So you see, I've drawn the curved, like the loop around the trajectories here, right? There is only a single solution. Like, no matter which case we are considering about, as long as the like speed ratio, like the velocity of the two players are fixed, there's only one solution for the optimal trajectory. So, but this optimal trajectory can rotate. I mean, like, it could be like this. It could be like this. But the difference between this one and this one is just they are rotated. But their shape looks exactly the same. So and Also, for these two different trajectories, it will lead to the difference of the final state. By final state, I mean the velocity of the players. For example, if the game follows this optimal trajectory, you'll find that the final velocity of the invader is like this, and the final defender's velocity is like this, right? But if the uh, optimal trajectory are like this, then the invader's final velocity will be in this direction, in the in this direction, and the final velocity of the defender will be in this direction. So you can take the like the terminal or the final velocity directions or final state of the players as one parameter of the optimal trajectory. Different final state, yeah, it will make the optimal trajectory different, but the difference is only a rotation. So this is the first thing. Another thing is that if we fix the rotation, right, that's the switch point between the straight line and the curved trajectory can be different. So it's like this. So if actually another thing to be mentioned is that um, when we solve this optimal trajectory, we did it backward in time. So it's like we first consider what are the possible terminal state. Here I mean like terminal velocities, right? And terminal locations. Given that, we just trace back to see how could the two players have come along to like we trace back to see how should the players have done such as they reach this terminal state eventually. So if we trace back, so we're showing here is that so if the defender if the invaders end up like this, right, it should have come along the curved trajectory and switched. It should have switched from the straight line trajectory at this location, right? But it can also have switched to the curved trajectory at a different position, for example here, and that will lead to a different straight line trajectory. And this defender also has its corresponding different straight line trajectory. So that will also make this whole optimal trajectory different. Okay, so this can be can be considered as a second parameter of the optimal trajectory. Okay, so this the thing that I want to explain. Um, so because our final goal is to like given the defendant location solve for the barrier that right. So as we mentioned, like the first parameter is how the game ends, and this is a description on how the game should end. It should satisfy these two conditions. Like for game one, the first is that the invader must be captured at the corner. Well, the reason is pretty simple. This is because like if this is deadline, right? If this is deadline, this is the target area. If the invader is captured here, if the invader is captured here, that means the invader is not doing its best. It can just go directly to the left more, then it will not be captured. So it's like the invader is not doing the best if it's not captured at the corner. And if invader is not doing its best if it is not captured at the deadline. And I think it's pretty easier to understand that it should be captured at the boundary of the target area, right? If the invader is captured here, that means the defender is not doing its best because we are looking at the situation that the defender just win the game. If the defender makes a little bit of change, then it's gonna lose. So apparently being captured here doesn't satisfy that situation. Yeah, so that's why it must be captured at the corner. And the second thing is that the final velocity must the angle between the final velocity of the two players must be larger or equal to than this value. So this is the angle such that like if this is the defender and this is capture range and this is the invader. So let's say if this is the velocity of the defender and this is the velocity of the invader. So this angle is the angle such that like this component of the invader is equal to the velocity of the defender. Because like when these two components are equal, that means just capture. So that's why we need to satisfy this. But this angle could be larger than this value. And that would mean the defender's velocity is larger than this component of the invader. But if at this moment the invader has reached the boundary of the target area, that also counts as just capture when the invader is entering. Right? Although there is capturing, not just capturing, but if it is captured a little bit later, then the invader should have already entered if the invader is at the boundary. So yeah, so that's the second condition that has to be satisfied. So there are like very many possible states that satisfy these two conditions. Then we're going to take all of them and solve for the cases such that take all of them and also change the second parameter, both of them, such to solve for the trajectory such that the trajectory passed through the defender's initial location. And then the corresponding invader's location will like draw out this line, and that line will be the barrier of the game. Okay. Yeah, so another thing to be mentioned is that I think let's just use this picture. So probably see like let's take it this order. Well, I mentioned that the location of the switching point between the two stages of the game can be different, right? If we start from the case where the players spend the longest time on the loop round stage, then we will have something like this. Okay, if we go to the extreme that the players takes the longest time on the curved trajectory, you will have and you solve for the trajectory that pass through defender's given location, right? You'll have the invader's corresponding location at this point. Then you gradually decrease the time the two players spent on the curved trajectory. Then the corresponding invader's location will move along this direction. So then you keep decreasing the time on the curved trajectory. What you feel like is that the invader's location draws this curve. And this curve is called this envelope barrier. Yeah, so at the end of the envelope barrier, you will find that the trajectory, you will find that there's no loop around the trajectory. everything is straight line. And that would be the end of the envelope barrier. So starting from this point, we switch to gradually increase this. Well, on the envelope barrier, the final angle between the defender and the invader's velocity is always equal to this one. Okay, and starting from the endpoint of the envelope barrier, you gradually increase the final angle between the two players to be larger and larger than this value. Then you will find that the invader's location will continue to draw the barrier, but it will end up as this yellow curve here, and that's called the natural barrier. Yeah, so that's basically the structure of the barrier. Yeah, I think so this is a brief process of how the barrier is solved. So we fix the defender location, and we change the switch point as I just described, and you will see that the invader's location gradually draw this barrier. Yeah, so this is how the barrier is solved, and then here comes the solution. The previous description only solves one branches here, but the thing is symmetric, right? If the invader is captured at this location, then we will have this barrier. But if the invader is captured here, we'll have this line. So this is it. So I've shown two possible defender locations. You can see that this distance between the two deadlines are different in this figure, and the distance between the defender and the target area is also different. And in the first case, there's an intersection between the barrier we solve, and only the part above the intersection point is effective. We should discard anything below, like this part doesn't count, like this two lines. So if the invader's initial location is here, oh yeah, and one thing to be mentioned is that the trajectories that we solved before, they are only about the situation where I would say the neutral outcome. So it's kind of a tie between the two players. The defender's not win, and the invader doesn't win. So it's kind of the tie. If the invader starts above there, like if the defender is here, if the defender is here and the invader is here, we do not have the solution for this case. So if we want to use the trajectories in this paper, then the defender can wait for the invader to reach this barrier. And only when the invader starts from the barrier do we have a solution. So just to mention that. But in this case, the defender cannot make any mistakes. If it changes, like if it makes slight error in following the optimal trajectory, then the invader will have a chance to win. So yeah, so if the defender wants to make sure it will always win, it's like a better strategy is to do something, like not just stand still when the invader is here, right? But we do not have the solution for this paper. I think this is also something that could be asked. So I just want to mention it here. Okay, anyways, yeah, so the other figure is a different case where the two branch of the barriers does not intersect. So here an important and interesting view to this problem is that here we can imagine, like if we imagine that the boundary of the target area is not here, but here, right? We can see that if the defender is still at this location, then the invader will still be captured here, right? But we've already assumed that the target area is here. So that means the invader being captured here means the defender win the game. Like it's not just a tie, but the defender win the game, right? If the target area is here. So, but if the target area is here, the distance between the defender and the target area will be larger than the original case, right? So this means that this distance between the defender and the target area is the smallest distance that the defender will not lose the game, given the distance between the deadlines. So that means there is a relationship, like for the defender not to lose the game, there's a relationship between the distance between the two deadlines and the distance between the defender and the target area. Right? You can see that this relationship is different in the second figure. So we can change the distance between the target area and distance between the defender and the target area, or the distance between deadlines and the distance between the defender and target area. We can change those two parameters to see how they are related, and that figure is given here. So this is the horizontal axis is the distance between the two deadlines, and the vertical distance is about the distance, like it's basically this distance. I put it as mean YD, that's because I've explained that it's the smallest distance for the defender to smallest distance between the defender and the target area, such that the defender do not lose the game. So that's why this minimum is put here. Okay, so like if we have an infinitely long boundary, like straight line target area, then that means we need a group of defenders to standing along it to defend this target area, right? So we can like divide this infinitely long target area into sections. If the invader like coming in here, then we'll let these two defenders to mirror each other's action along this dashed line. So that way, this line will act as a deadline. Right, so this figure will give us a guideline to choose the distance between the defenders and the distance between these defenders and the target area. So to choose this distance and this distance, they are related. So yeah, so I think that's the significance, or like that's what's valuable of my research, of this paper. I think is to give us a guideline to allocate the defenders along the target area so as to protect this target area. So above are the solution for the first case. I think I've said too much about it, but I just want to make everything clear. So for the second game, I just directly gave the result because the solution process is similar. It's different, but similar, very similar. The idea is the same. But the result is that we still have two things related. The first is still the distance between the defender and the target area. But here we use polar coordinates. So it's basically the distance between the target area, the center of the target area, which the target area is a circle. Center of the target area and the defender, this distance. It's similar to this vertical axis here, right? But a different thing about the circular target area is that the barrier that we can solve for a single defender, it just ends at some point. It's not going to stretch anymore. So it's not like what we've shown here. So this is what we expected, right? But eventually I find that it's not like that. It cannot be enclosed. It ends somewhere here. It's just because during the solution, we are going to change the two parameters, right? One of them is the terminal velocities of the two players. The other is the switch point between the two stages, right? So no matter how much you change them, like those two parameters also have their like range. You cannot go infinite. You cannot spend infinite time on the curved trajectory. So they have some ranges. Even though you like go over all the possibilities of that two parameters, you still cannot have this enclosed curve of the barrier. So that's this endpoint of the barrier. So yeah, it's just like that. However, there are endpoints, right? But this angle, right, this central angle. So these 2 points will define a central angle. The role of this angle is just like the distance between the two deadlines in this first case. So similar to this figure here, we can also draw a figure for the second game. And the horizontal axis is the distance between the defender and the center of the target area, which is raw D. Basically, it's raw D here. And the vertical axis is actually this angle. Is actually this angle. This angle. But I put it as angle max. That's because it is the largest portion. It is the largest portion of the circular target area that can be defended by a single defender, single slower defender, given raw D, given the distance between the defender and the target area. Okay, so we can have this curve here. So basically, using this angle, so if imagine we put the defenders evenly around the target area, then this angle will give us a guideline on how many defenders are needed, right? Given the like if we fix the distance between the defender and target area. So similarly, the takeaway and message here is that the solution will also give us a guideline about allocating the defenders around the target area. So I think that's a useful conclusion of this paper. So so finally we come to the conclusion that this paper discusses the possibility of defending target area with a slower defender. And we found two possible solutions. And for both cases, we solved the barrier, and which gave us a guideline of allocating the defenders. Yeah, so that's of the presentation. So I think I've talked too much, but I just wanna give you like more details that like for better understand. So if anyone asks questions, like you can handle them. So I hope you get to understand it. Oh yeah, there's another thing. In this figure, you can see there are some black circles here. This dashed black line and this black line. This solid black line. So I've mentioned that the invaders will end up rotating around the target area like permanently. The game is never gonna end. So the radius of the invader rotating around the target area is limited. It cannot be infinitely small. It cannot be infinitely large. So the dashed black line here is the largest, gives the largest orbit that the invader can rotate around target area. And also this one is the dashed, the solid black line is the smallest orbit that the invader can rotate around target area, just in case someone asks. So actually, this figure comes from, I take it directly from my thesis. My thesis have more explanation about this, and also this this bar delta. Like if just in case someone ask this, I think you can say it's some like detailed intermediate parameter variable that I use in the paper. If they want more details, they can read the paper or search for my PhD thesis. Yeah, so okay. Yeah, so I think that's all that I think I have to say. So if you have any questions, just contact me. Just send me email. I will be checking my email regularly. Um, yeah, so thank you. That's all of it.